So my name's Julie Pinto. I'm a PhD student at Murdoch University. My supervisors are Dr. Magni, Dr. O'Brien, and Dr. Dato. And today the title of my talk is the wing beat frequency of calyptrate flies. So the wing beat frequency research has mainly focused on mosquitoes at this point. There's a lot of data with mosquitoes. There's been some research done on flies. There's been some research done on flies, not a lot. If there is research, it's only a couple of species, and it's not over the same conditions. So what I aimed to do was to record the wing beat frequency or a number of species in the same conditions. So a lot of the research on wing beat frequency in the past has been done acoustically. There's been some research done with tethered flies where they tie them and record it that way, and then also free flying flies. And this is a pretty common setup down the bottom here where you have the recording chamber with the insect inside of it with the recorder. The problem with acoustic recordings in the past is that there's a lot of noise that comes along with it. And because the wing beat is so quiet, it's difficult to remove that noise from the recording. However, with the research I've done, I've demonstrated that the software and hardware has come a long way, and it is actually possible now to record it acoustically. And I'll show that a little later on. So I feel like a lot of people have given up on the acoustic, but I feel like we should go back to it. A lot of the research for wing beat now is focusing on optical sensors, mainly in the agricultural field. They use the system where photodiodes are set up, where they project a laser, the insect flies in between, disrupts that signal, and that's how the wing beat frequency is recorded. With this, it's also being used in conjunction with deep learning, so a lot of algorithms to help further classify the insects. This kind of recording does not have the same problem with noise. However, there's additional problems. The optical sensor I tried had the problem with the flies would not fly through the sensor, but rather they would land on the edge and then walk through the sensor. So that's one thing they're figuring out right now. But in the meantime, we do have the acoustic. So the 4 species that I recorded the wing beat of were across 4 genera. There was the Sarcophagia, the flesh flies, the Caliphora dubia, the Ocilia sericata, and then to represent the muscadaes, the Australian bushfly. So flies experienced 3 episodes of rapid radiation, most recently around 65 million years ago with the Schizophora, which gave rise to the calyptrates. They saw that rapid radiation of species, and this includes the common and widespread flies that I researched, such as the house flies, the blowflies, and the flesh flies. So we know that insects evolved flight around 400 million years ago, and this is supported by fossil evidence. For example, the winged hexapod, which was from approximately 325 years ago. So much of the success and diversification of insects, and including the rapid radiation of calyptrates, is a result of the evolution of flight, but also the miniaturization of the body size. However, the problem arose where the smaller your body became, the faster you had to flap your wings to generate sufficient aerodynamic force to stay aloft. It also meant that you need to evolve by having a sensory motor system that provided fast sensory feedback to keep up with this fast flight. So as a result, we saw the evolution of mechanically gated flight muscle and the development of a separate steering motor system. So along came the asynchronous flight muscle, which 75% of insects now have this type of muscles. But this adaptation enabled that very high wing beat frequency, which you see in flies. So you have 2 pairs of antagonistic asynchronous muscles. As one pair contracts, it deforms the thorax so much that it results in the stretching of the other pair, causing the second pair to contract. So you see that oscillation. So the neural signal is only needed to initiate. So the cycle of stretching and contracting is repeated at high frequency, with the low frequency stimulating impulse from motor neuron nerves So you're not relying so much on the neural signal. So this enabled that very high wing beat frequency you see in flies and other insects. So we can see how this affected the wing beat frequency depending on body size. We also know that temperature and the age of flies is affects wing beat frequency. So those are some of the variables I sought to standardize. So when you have flies that are flying so quickly with their superior flight, it presented a couple of problems with trying to record their wing beat sounds. They're a little different to other research that's been done on mosquitoes and bees, which tend to hang around when you're recording them. But I quickly found out when trying to record flies, they were flying around like maniacs. I put them in a recording chamber and they tended to repeatedly bang into the signs and create a whole lot of sound. And they definitely needed a bigger space to fly. So what I resorted to is releasing a single fly into a 10 by 10 foot room. I had a single light source, so I darkened the room and found that the flies would most of the time fly around the fly, around the light. And that enabled me quite successfully to record their wing beat sounds. So I standardized the methodology so that all flies recorded were 3 days old. The room temperature was set at 25 degrees Celsius, and a wet towel was put in the room to try and keep the humidity the same. So with any noise that you're recording, you will see what's called the fundamental frequency or pitch, in addition to the harmonics, which come at higher rates. So for the purpose of my research, I was looking at only the fundamental frequency, and I was using that to classify the species. So what I did was I put the pupae in a 10-gallon container that enabled the flies, once they emerged, to have enough room to practice flying, so that when I recorded them, it wasn't the first time they were flying. Once emerged, they had access to only sugar and water. And because the sexes were mixed, it's possible that many of the flies were mated at the time of recording. So I recorded individual flies for approximately 1.5 minutes. And at the end of the recording, I captured them and confirmed their sex and species. So I used a relatively inexpensive voice recorder, not like the ones of the past. I used a Sony recorder, which was around $200. I was able to record a WAV file. I brought this recording into Audacity, which is a free software. Now, before I recorded the wing beat sound, I recorded an example of ambient noise and used that as a noise profile, and then extracted that from the entire waveform. This enabled me to remove a lot of the noise and made it so it was mainly the wing beat sound. I then went along and removed anything that wasn't wing beats. For example, the clicks from the voice recorder made a very loud sound. Any bumps, anything like that was removed. And then once the waveform was cleaned and trimmed, I then brought into a linguistic software called Pratt. I was very fortunate to find this software. I didn't know about it until I started this project, but it turns out that human speech is very similar to the wing beat frequency of flies. Who knew? So it's around 100 to 300. So it was excellent for finding the pitch or fundamental frequency of that wing beat sound. So they used the auto correction function in that software. And so I was able to bring it in, and from that, able to find the mean fundamental frequency. The auto correction algorithm is excellent for finding a certain signal within a lot of noise. And that was certainly the case. It's amazing how much ambient noise is there when you record. So the algorithm finds repeating patterns. It finds that wing beat sound. And even if the fundamental frequency is missing in certain parts, it's able to deduce from the harmonics what that fundamental frequency is. So the algorithm was able to use the noisy data and turn it into a signal which showed that waveform of the fundamental frequency. So I did have to change the defaults in the linguistic software. Obviously, the wing beat sound is very quiet compared to human voice. So I had to increase the silence threshold to allow more of that noise in, but that worked quite well. And just to show you how much data you acquire from a 1.5 minute recording, the box at the top is the entire 1.5 minute recording. If you take a section out of that, you can see the actual buzzes. So these blackbirds here are buzz, buzz, buzz. if you take just one of the buzzes, it turned out this is 0.3 of a second. These are complete cycles of the wing beat. And this is just from that 0.3 of a second, how much data you acquire. So I plotted all the data together. I found that across the 4 species, the wing beat frequency was significantly different. And what you see is a very nice, you can see that trend with the smaller body size resulting in a higher fundamental frequency. So you can see the Australian bushfly is a lot smaller than, say, the flesh fly, which is at the other end. And this results in a much higher fundamental frequency. And you can see clearly as the size of the fly increased from flesh fly to dubia to sericata and then the bushfly, as the size increased, as the size of the fly decreased, the fundamental frequency increased to compensate. So the fly is able to keep aloft. So I separated by sex, and I could see that there were differences between the males and females. For the first 3 species, it was clear that the females had a lower wing beat frequency than the male counterpart. However, when I got to the Australian bushfly, this was a little different. It was apparent that the females actually had a higher wing beat frequency. I don't want to say why this is so, but just from my observations, we know that the diet is very different. These first 3, they're scavengers, they eat meat basically, and then the bushfly is it lives and feeds in dung. And also when recording the first 3, they seem to zip around the room very fast. With the bushflies, as most people know, they tended to stick around and they still flew around the whole room, but not as much. So that may be one of the reasons, either diet or behavioral. I also looked quickly at age. I recorded a further 20 species of Calliphora dubia, and you can see it around 180 at the 3-day old fly, that most of those wing beats are around equally distributed around the 180 hertz mark. But as they get older, to the 5-day mark, you can see the higher frequency. So it'd be interesting to see at what point that levels out. And certainly I would need to collect more recordings than that 20 flies. However, this is something to look at. So, sorry. So from the data, it's clear that you can still use the acoustic method. Certainly with advances in hardware and software, you are able to isolate that wing beat frequency. And this is definitely an excellent foundation for using this kind of methodology to classify calyptrates further by making further adjustments, and so that you can clearly see the means across the wing beats. And obviously there is a lot of overlap, which is the same as what you see with mosquitoes, with other species, but certainly the mean fundamental frequency is different across the species. So that concludes my talk, and if anyone has any questions, I'm happy to answer them.
Thanks so much, Julie. Are there any questions for Julie? I know you kept you're very conscious of keeping lots of the variables the same throughout your experiments. Do you think once all those variables are taken into account, kind of in the real world of trying to identify a fly using wing beats, you'll still be able to get these kind of clear differences in the means?
I think so. I work in the forensic field, so it's not uncommon for us to make it very clear that we need to know the temperature of when these larvae were collected and what they were exposed to. So it would be a similar kind of scenario where if I were to try and classify the flies in the field, I would need to know the temperature, and also the age of the flies is important. So if there's a crime scene and you're looking for new flies, then you would be certainly looking for that wing beat of that certain hertz. So definitely.
Thanks, Julie. Any other questions? No? Well, join me in thanking Julie. And Julie, if you're happy to stop sharing your screen in a sec, that would be awesome.